So great to talk to you here at PGConf. My name is Vaijayanti Bharadwaj. I work for Enterprise DB. And today I'll be talking about Postgres and its full text search capabilities and its comparison and a comparison with Elasticsearch. A little bit about me. I have a background in storage, file systems, distributed systems, databases. I've authored a book on database transactions and concurrency control. About today's topic, so a little bit of background about full text search. So with analytics and anomaly detection, etc., becoming very important today, full text search has a lot of use and applicability. A lot of data is becoming descriptive. Postgres has JSON and JSONB as its data types, and a lot of fields are descriptive, and it's important to be able to index and search in this area. I have worked prior to this on e-discovery platforms, and in cases of e-discovery and compliance, intelligent searches become very, very important. It's things like finding similar documents is a very important use case. Similarly, with applications becoming highly distributed, and there being tremendous amount of information in logs, full text search becomes very, very important for these use cases where you need logs for debuggability, generating alerts, and so on. A little bit of background in this space. So, full text search, when we say full text search, Lucene, Elasticsearch, and Solar immediately come to mind. Some of these engines, especially Elasticsearch, is what I'm going to talk about in my talk today. They have denormalized data models in the sense that there is not a lot of focus on normalization. So many-to-one or one-to-many relationships are represented by nesting objects and so on. It is sometimes difficult to capture many-to-many relationships because these data stores don't do joins. It is the application which has to do in case you have such relationships. But a lot of applications do not need normalization. These engines do not typically give ACID semantics. Typically, atomicity is at a record level. Idempotency has to be taken care of by the application. So if you're inserting a batch and you fail halfway, you have to undo or redo yourself with your own mechanisms. Concurrent updates. Elasticsearch does provide ways for concurrent updates in terms of having version numbers to the documents, and as a application, you have to compare the version number, and there's an error if you are updating with a lower version number, and so on. But this is based on the assumption that updates are not very frequent, multiple threads are not simultaneously updating, and so on. Having said that, a lot of applications which use Elasticsearch typically may have append-only data like logs or postings lists or emails and so on, and updates and modifications are not common. Making a case for databases for full text search, many times a lot of fields, a lot of columns in a database are descriptive, such as a summary or a description, some JSON columns, and so on. And creating a separate data store for these is typically, it may not be a good idea because it needs maintenance. If you are carrying out certain set of batching operations in the database, they may not occur in a transaction in Elasticsearch, and you may have to account for inconsistent views among the two data stores, stale data, dangling pointers, and so on. SQL is a powerful query language. It has, and it's especially good when the terms to be searched for are precise. When combined with full text search, it can make up for a very powerful query language. You could do full text search, temporal, spatial, graph queries all in one. Databases are naturally good at supporting many-to-many relationships, joins, and so on. And again, the ability to do full text search along with all this is very, very convenient. And obviously, databases are great at giving asset semantics. That's the main focus. And it's great to have that with your full text search. And of course, the traditional features of databases like access control and so on, becomes helpful when you want different users, for example, to see different search results and so on. The goal of today's talk, Elasticsearch is one of the leading search, full text and search engines. And for Postgres, this is an adjacent capability. But the goal here is to see how far can Postgres go with respect to its full text search capabilities. We compare the indexing and search performance with a data set like Wikipedia data, which is extremely text heavy, and which is like a normal data set for Elasticsearch, but it's something not commonly done with Postgres, and we want to see the extent to which Postgres takes us. We highlight some limitations of Postgres in this area, and we end with some conclusions and recommendations. So, how many of you here are familiar with Lucy in Elasticsearch? Some of you, all right. And how many of you have used the full text capabilities of Postgres? Okay, great. So I'll give a brief introduction to these capabilities. The goal is not to dive very deep into it, but it is to bring everybody on the same page here. So we all know operators like, I like, the regular expression operator, and so on. But what is the problem with these operators? They typically they are not indexed. You have to do a full scan to be able to find matches. Secondly, there is a language-specific aspect to it. For example, if I want to search on, say, financial crisis, I should be able to match finance crisis also, finances crisis, or variations of that word, which is very language-specific. So this is what we get with full-text search. This is different for different languages. For example, the way these terms are normalized in different languages and tokenized and broken down is different for different languages. There are a lot of irrelevant words like a, and, I'm sorry, the, and so on, which need to be removed. And this is again language dependent. Then basically, one of the very important features in full text search is the ranking of results. For example, I may want to say that if financial crisis comes in the title, it has a higher rank than it comes in the content. If it is found exactly as it is, it should have more rank. So there is a way to rank how well it ranks with the given query. It's very important to index it, because doing full table scans is very, very expensive. And I talked about boosting of fields. Also, many times it is important to have synonym. We may be searching for something, but we may want to look for synonyms as well. So the ability to have maybe domain-specific synonyms, for example, if you are in a finance domain or a sports domain, the synonyms could be different. So these are the features of full-text search, and we take a look at how Postgres does it. I'll just a brief introduction to the terminology here. A document, a lot of NoSQL and even in Elasticsearch, a document is what we would consider equivalent to a row. It can have some columns or fields which are precisely searchable. For example, product ID. You may not want to break it down, but product ID is precisely searchable as it is. It's called as keyword, type keyword in Elasticsearch, but other things like a name or a title or a subject could be full text, and the type there is text. Tokens. So whenever you have a lot of text, you need to break it down into tokens, and you could have different tokenizers. For example, a file path needs to be broken down differently. A URL is broken down differently than normal text. Lexemes. This word is used pretty frequently. So we first have a set of tokens, and after that, the tokens are passed to a dictionary. A dictionary will eliminate some of them. It will it may replace it with synonyms, and it will normalize it or stem. Stemming is the word. There are various stemming algorithms. It may stem it, normalize it, and create an array of lexemes. And this array is sorted by the lexicographic order of the lexeme itself. Lexemes, the dictionaries retain the position information because we want to do adjacent searches as well, and we'll see about that. As we can see here, dictionaries and parsers are language specific, and Postgres supports a bunch of languages. Just to give an example, there is a random text here, and we can see how the tokenizer has broken it down. So there are some tokens which are ASCII tokens, like cats. Some are numeric tokens, some are alphanumeric, and there are hyphenated tokens. So different types of tokens are generated. Talking about lexemes, having broken down these tokens, here we see the impact of, we see the effect of both tokenizer as well as dictionaries. So this text has been passed through tokenizers and dictionaries, and the output is the last column that you see here. So some words have been, and that is an array of lexemes which is generated. So some words have been eliminated, like whatever are the blanks, whatever are punctuation marks, etc. have been eliminated, and what we get is an array of lexemes here. There is a default configuration in Postgres. It supports, like I said, many languages like English, Chinese, Russian, Hindi, and so on. For English, the default configuration is set to English here, and we have two types of dictionaries, the English stem and simple, which come into play for different types of tokens, and these primarily constitute. There is a way to change this configuration, and you could download advanced dictionaries like iSpell and so on, and use it as well, and change the configuration to what you have. Or if you are working in a specific domain, you can have your own synonyms dictionary and so on. And typically dictionaries are chained, so you can have a synonym dictionary at the beginning and so on. So I'll not go into details of changing configuration. It's extremely well documented on Postgres documentation. We look at some tools. One is, so tsvector is a data type, and it basically is an array of lexemes with positional information, right? And tsquery is what is a full text query in Postgres, which has Boolean operators, precedence operators, and all these things. If you want to convert text, you use something like 2tsvector. You can note here that one of the arguments to this 2tsvector function is English, which is a configuration we saw before. If this is skipped, it takes up the default. And the second argument is either a text column name or a bunch of text that you can give to it. tsquery also needs a configuration because the query is also passed. And the expression tsvector at, the operator at says, does this vector satisfy this query? Right, we'll see this with examples later, but these are the primitives. So basically, we have a function to convert text into tsvector. We have a query and we have an operator. JSON can also be converted to tsvector, and you could say that ignore the numeric fields in the JSON and so on. But I'm not going into those details for keeping it brief. This is just an example here. This is an array of lexemes which is formed from some random text here. You can see that there is positional information. The number 2 comes at position 7. Bruno comes at position 1. The apostrophe and the S has been removed. And position 2 is missing here because it has removed the S at position 2. So some positions are missing, and finally you get an array of lexemes. And you can see that there's a 2tsvector. Does it satisfy? Does this vector satisfy this query? And the answer is true. All right. So coming to the experiment, right? So I took the Wikipedia data set, only the English one and the latest versions of Wikipedia. And I primarily took the titles and a few fields. And this is the schema. About 11.7 million documents were collected, and I had to truncate some part of it because Rest of it was going into references and bunch of things. So this is the schema, and the key here is the titles and content. These are two text fields. Titles being a small, there are many Wikipedia pages which point to the same content. So titles can be a bunch of titles. So here, if you note it, I'm using a GIN index, and I'll talk about it briefly. But this expression in the GIN index, right? So what this expression is essentially saying, convert titles using a simple configuration to a TS vector, and convert content using English configuration. See, I could have created two GIN indexes, one for title and one for content. But many times, one wants to search for a word irrespective of where it occurs, right? To be able to do that, there is one GIN index, but I have given a weight of A to titles and B to content. These weights are implicit, and they have a certain weight, like A carries a weight of 1 and B carries a weight of 0.4, but I can change it. I could give a third argument here and say that A should carry this weight and so on. It's modifiable. But essentially what happens is that the array of lexemes which is generated gets labeled whether this lexeme came from A or it came from B. So if I have to search, if I'm only interested in a title search, my query, I could say that just look at it in A. But if I don't care, then I'll not say anything. So the important thing to note here is that I'm using an expression in the GIN index, but this is not a good way to index, especially a large data set like this, because when I run this query, when I run a search, it will find a match in the GIN index, but to verify if that match exists, it has to convert that row to TS vector again, which is very expensive. So this is not a viable option for indexing, because queries could go into tens or 20, many seconds. So the second option is to add a column, which is a generated column. I think since 9.2 Postgres supports generated columns, and I'm generating a TS vector column on the fly. You could also write a trigger, but this is more convenient. And essentially it is adding another column called FTS, which is of type TS vector. And you are simply giving FTS to the GIN index. So the thing with this is that if you get a hit in the index, the lexemes are already present in FTS. And you don't have to reevaluate the lexemes using a parser and a dictionary. So this is the way I have gone with. And we'll talk a little bit about GIN index and some of its limitations later. But this is an example of with a query. Let's say that we want to find all relevant documents which discuss US nuclear policy. So, I could say that use a TS query like US or USA United adjacent to states. And if you see that operator, it says adjacent. And if you see the number 2 in the operator between states in America, it means with a gap of 2, and so on. So search for this and rank it. And a TS headline, it's a function I did not talk about before. It basically takes the row and highlights the matching thing in that row. Highlighting is a feature offered by all search engines where they highlight what matched. So, you get a result such as this. So as you can see, things with nuclear and policy coming in the title, it's ranked higher. And you get many such results. Elasticsearch, my goal is not to deep dive into Elasticsearch, but this is the schema that I have used with Elasticsearch. It uses a JSON language to express schema. I do not have to tell Elasticsearch any schema. It can infer the schema, but I have chosen to write it here. You can specify a mapping, and this is the mapping. Elasticsearch, whenever it sees type text, it uses analyzer, which is a combination of tokenizer, dictionary, etc. And the most common one is standard analyzer. It works out of the box most of the cases. And changing this is to be done with caution, because you may not get good matches if you change it. It has a lot of repercussions. So this is the schema. And I would like to talk here about the results. Right. So I have run an experiment where I have 8 processes parallelly ingesting a simplified form of the data into Postgres 15. and the same form of data is ingested parallelly by 8 threads into Elasticsearch. And I have done a comparison, and here are some of the results that I would like to talk to you about. So I want to first explain the top row. So Postgres with gin inline means that the index is created in the beginning, and while we are inserting into the rows, the index is also being inserted into. Postgres with gin offline means I create the index at the end after all insertion is done. And the Elasticsearch is Elasticsearch column. If you notice, the bottom row is the size of the table plus the index. So the size of the table, this data set, like I said, is about 9.5 gigabytes. If you see the data in Postgres, the table size is 15 gigabytes. Out of so if you recollect, we had to add a tsvector column, which kind of accounts for almost 8 GB of this table size, and 14 GB is the index size, which is pretty big. When I create the index offline, the index is very compact, and in the prior case, the index has a lot of half-empty pages, which is causing it to get bloated up. In the offline indexing, it gets filled up, and it's pretty compact. One of the things that I wanted to note here is that the CPU consumption. Elasticsearch very efficiently utilizes all the CPUs. However, what I've seen when Postgres ingests the data, the first phase of insertion is utilizing 90+% CPU, but in a gin index, the insert is a little. I just want to show you how a gin index would look like for. Is this visible? So a gin index, basically the key is the term. It is the term, right? This is taken from a pretty famous blog. It's a very good picture showing how gin index looks like. So, for example, hello world. So hello will be the key, and all the documents where you find hello, the 02 here, the tuple you see, it is the page location and the offset in the page, the line item in the page. So you can see here that, and that is called the postings list in search engines, which means that where all this term occurs. And in some rare words, the posting, like zebra, the posting list may consist of 2-3 items, but for a word like, say, world may occur in 1 million documents, and the postings list consists of 1 million locations where this occurs. So there are 2 trees essentially. One is the tree of the terms, and the second is the tree of the postings list. So to insert here is expensive. So what is done is that there is a flat list which is sorted, and as you get your terms, you keep inserting, you just keep appending to that. This page list is sorted and then inserted in a batched way in the gin index. So what happens, the number I was referring to here, the CPU consumption is good in the first insert phase, but when the pending list is being put inside the index, the CPU consumption is very low, and this process takes considerable time. Therefore, the average CPU utilization is less. In the case of Postgres with offline indexing, the index creation is is run just in one process, and the CPU consumption is low. That's why the average CPU consumption in the first 2 columns is lower. And as you can see, the writes are very high because the size of the data is higher. So moving to search, right? The search is done by 64 processes running 10,000 queries each. These queries are of type phrase queries. So phrase queries require you to check the position of where this term occurs. So if I want to say hello adjacent to world, hello should occur in the document next to world, right? So it has to, in the gin index, position information is not stored in the index. So it has to, for every match you get, it has to go to the row and check for the positions and then take a call. So searches are slower. So if you can see that Elasticsearch is doing about 421 searches a second, but Postgres is doing 37. CPU is pegged to 100%, right? The disks, one of the like we saw, the Elasticsearch index is compact, and it caches the index, and thereafter it doesn't need to go anywhere else. So the obviously reads are pretty high in the Postgres case. So the other experiment that I wanted to do was to use a RUM index. A RUM index is available as an extension, and what it does is, it is similar to GIN, but the postings list has position information in it. So one does not have to go to the heap and look at the rows. You can get everything you want in the GIN. This system that I've used here for the first set of experiments provides very high IOPS. It's capable of it's capable of giving several tens of thousands of IOPS. I had to move to a Ubuntu system here with slower SSDs, and you can see the impact of using slower disk on the GIN index. So this is insertion. Again, 8 parallel processes inserting, but the disks are slower. And the first column shows that the slower disks are thrashing pretty badly. And Elasticsearch does pretty well even with slower disks. You can see that RUM takes some time to build. Yes, the disk usage writes per second is pretty high. And the utilization is also pretty high of the disk. Having seen this, I just want to look at the search here, right? So GIN does 14 queries a second, and the search here is slower than the first experiment because the disks are slow, and a lot of the searches are going to disk. RUM, while it gives 5 times better results than GIN, is still about 4 times slower than Elasticsearch. If you can see here, the reads are pretty high. A lot of the reads and the IOs here are kind of random because that's how the GIN tree is. So you can see that the average size of the data read is pretty small. Whereas Elasticsearch, the reads are somewhat minimized. It's just the time taken to cache the initial index. That's pretty much it. I wanted to move to this slide with a qualitative comparison of the features. So I have done a basic comparison, and with respect to queries such as and or precedence operators, both Postgres as well as Elasticsearch are almost the same. They both have phrase queries, a slop of n, like if I want to search for 1 gallon milk, I should be able to match 1 gallon soy milk as well as 1 gallon almond milk. That's a slop of 1. So Postgres supports a slop of exact 1, whereas Elastic supports 1 to n, which is far more flexible. You can configure the defaults in Postgres by adding synonym dictionaries. Elasticsearch has synonyms out of the box. Elasticsearch is something like this word comes somewhere after this, which Postgres doesn't have. Highlighting is there in both. Aggregations and sorting, it's there in both. Customizability is full and fairly well documented in Postgres. In Elasticsearch, out-of-the-box capabilities work fairly well. Customization is not that well documented. And of course, Postgres does not infer the schemas. In Elasticsearch, even if you don't give any schema, it infers it. If it finds out it's a numeric, it will treat it as a numeric. If it's a date, it's a date. And the rest is treated as text. Elasticsearch does provide some advanced features which I have not listed here. This is more from a point of basic features that are needed for full text search. For example, things like, if you say NY city in Elasticsearch, it will expand it to New and York and city with the appropriate operators and do a match, etc., which in Postgres you will have to say that yourself explicitly. So this is a qualitative comparison. And I wanted to, I have spoken about the GIN index and RUM index briefly, but I just want to explain what I meant by that. So if I want to search for documents with, say, nuclear and policy, right? This may not be very well visible, but I'll speak it out for you. What this essentially means is that in GIN, even though you get a hit in the index, you have to go to the heap and check the rows because you need location to know whether they are adjacent to each other. So imagine that a word like world may be very common, and you may have to go to 10,000 rows to check it. But RAM has all this information in the index, and it's faster because it just looks at the index, and that's it. So I want to bring some of the observations here, right? So some of the things that Elasticsearch does well is that its indexes are extremely compact. And it does a conversion of all the strings, like row IDs are called doc IDs, and all the lexemes are given IDs. So everything is an integer, and you can do run length encoding and a lot of things like that to highly compact it. So you can see that Elasticsearch indexes are extremely compact, and their goal is that in one lookup, you should get to your data. So at most, the queries take one disk lookup. So use of things like incremental doc IDs definitely helps very rapid traversal of postings lists. Skip lists are used for posting lists. Elasticsearch LSM tree indexes, they naturally amortize the cost of inserts by batching and doing periodic compaction. So you are not trying to insert everything, every single of these into B tree, which may be splitting and so on. You're kind of accumulating in memory, and it gets full, it gets written in a sorted manner, and in the background, compaction is happening. And this kind of lends itself well to parallelism because there is less contention. What I have seen with GIN and RAM indexes is that the indexes are large in size, much bigger, like the data is about 8 GB, but indexes are typically like 15 GB. The difference in performance between Elasticsearch and Postgres is not that obvious on very good SSDs because the SSDs are able to absorb the cost of I/O, but they are very stark on slower disks. So on slower disks, we saw that writes and reads were thrashing quite badly because they were random access, multiple random reads and writes for a single search and so on. Even if the index gets cached in memory, searches require heap lookups to perform matches and to perform ranking. High disk utilization is seen on slower disks. The pending list is an option in the GIN index to amortize the cost of inserts, but cleanup of the pending list does not take advantage of parallelism and is seen to take quite a long time. The disk as well as CPU utilization is pretty low during this phase. I'm sorry. Yes, so when indexing is done offline, like you first insert the data and then you index, the indexes are smaller with GIN and pretty compact. And this can help searches because index is likely to get cached in memory. However, the data may not be in memory. What we saw was that the tsvector had to be stored as an additional field for non-trivial sizes. And this does bloat up the whole data. RAM speeds up the search about 5 times compared to GIN, but it is still about 4 times slower than Elasticsearch. And RAM indexes are surprisingly compact as compared to GIN. Yeah, these are some of the observations. And lastly, I want to conclude here by saying that Postgres, as a database, has obviously focused on OLTP and ACID semantics, and full text search is a little less used and a less known feature, and maybe less worked on feature of Postgres. Having said that, it offers fairly rich and well-documented customizability. Its feature set and language support match up to a considerable extent to a very evolved and specialized engine like Elasticsearch. And I believe that with the JSON data type becoming more and more common, definitely full text search is going to be a more and more used feature of Postgres, and therefore some things need to be looked at, like compacting the data and the index sizes for use cases such as these, improving the index throughput. Maybe Postgres allows for writing of indexes as an extension, which is a great capability. And searching needs to be improved on in terms of putting more data in the indexes so that the rows don't have to be looked at. Basically, something like the RAM index, but an improved version of it. So this is all I had, and I'll open up for questions.
Questions?
I saw that first you show CPU using 95%. You have one slide where you show the CPU using 95% on one side. That's I guess the next one, yeah. Yeah, you see there like Elasticsearch is using 95% of the CPU. Have you tried to just use more parallelized search on Postgres to do this kind of benchmark and see if Postgres maybe is slow because like we have some I/O waiting time and blocking, and then maybe it would compensate in parallel processing.
Sorry, I've tried to use what?
Okay.
I didn't really get your second part of the...
Yeah, so basically when I see this slide, I see the CPU percentage that PG is using less CPU percentage, right? So it means that if you throw parallel process in both cases and try to compare, maybe Postgres will reach more closer to Elastic because some I/O waiting time, right? So my question is, have you tried to benchmark parallel searching just to see if like parallelizing the search would bring any benefit?
Yes, that's a good point. So one thing I want to say here is that the CPU percentage is an average of 2 phases. Like I said, almost Postgres takes about 1200 seconds to do the indexing, but it almost takes 1000 seconds to clean up the GIN spending list, and that is a process which utilizes very less. I mean, it takes 15% CPU, and it's a single. So the average CPU percentage is very low. The insertion is fairly high on CPU. It's about 90%. And yes, I do agree that it is perhaps the waiting time because of the disk accesses and so on. Yes.
Yeah, so I was just thinking like, so Postgres is not that bad if we think on this case, right?
Yes, I just want to, the processing of the GIN pending list needs to be definitely made faster, and I think here it's not that bad with respect to Elasticsearch, yes.
Yeah, thank you.
We have time to take one more question.
Hi. So on one of the slides, you showed that if the search term appears in the title, it shows at the top. So do we have some kind of tuning where we can do reach and relevance kind, like the search term appears maximum times on a particular page instead of in the content instead of the title. So if I want to list the pages that has the search term maximum time, not in the title but in the page, so can we provide that tuning?
Yes, if you want to search only in the content and not the title.
Yeah, but it may appear in title also, but in content I want maximum reach of the particular term.
You can change the weights of that you have given to that. There was a set weight call, and you could change the weights. Does that answer your question?
Yeah, sure. Thank you.
Thank you, Vaijayanti.